In this set of videos, we're going to talk about how to evaluate the data presented in a scientific paper. Peer review, which we talked about in week number 4, is an important process, and you can think of it as the first gatekeeper in whether or not scientific information should even be published. However, it's definitely not fail-safe, and papers with poor data still sometimes get published. My goal in these videos is to give you some strategies and overall steps so you can really critically examine the data presented in a scientific paper and not just accept what the authors claim at face value. Specifically, after these videos, you should be able to 1. Identify the signs of reproducible or high-quality data. 2. Identify the signs of data that is of poor quality or that might be presented in a misleading way. And 3. Critically evaluate data representations. To start thinking about how to deal with data, let's think of a hypothetical experiment looking at the efficacy of a drug, called drug A here, in lowering cholesterol levels. We've designed a randomized, double-blind, placebo-controlled study where participants are divided into 2 groups, with one group taking drug A daily and the other one taking a placebo. We measure initial cholesterol levels for all subjects in each group to show that all are starting at a similar point. We then remeasure cholesterol levels for all participants 1 month later, looking to see if there is a difference between the experimental and control group. The way you would present your results could look something like this: a table where we are reporting the average cholesterol level, LDL level, for each group at baseline, and again 1 month later. We can see that the experimental group does indeed have a lower average cholesterol level. However, if we're going to report this in a scientific publication, reporting the average alone wouldn't be enough. We would need to include additional information. Here's why. This slide shows 2 sets of data, set number 1 and set number 2, both with an average value of 11.8. That average is plotted on the graph to the right. However, notice that data set number 1 has a fairly small range of values, 8 through 16, while set number 2 has a much wider range of variation, from 2 to 35. This variation can be captured in a statistical measurement called the standard deviation, which is one way to measure variation within a data set. In this case, we can see that the standard deviation for set number 2 is much higher than for set number 1. Standard deviation is frequently shown on a bar graph as error bars. This is therefore one way to evaluate data presented on a graph. If we add the error bars here, we can see that set number 1 has much more consistent values because the error bars indicate so. The lower your standard deviation, the more reproducible or consistent your data is. Remember that in science, the strength of data comes from when those observations can be made reproducibly. The large standard deviation for set number 2 is a measure of how inconsistent the data is. Let's look at a real example of this, one that is a particularly bad example. This is a study in which the authors obtained brain tissue samples from a tissue bank, specifically from individuals with autism. They then took each sample, isolated tissue from specific lobes in the brain, separated each tissue sample into 3 pieces, and then measured the amount of aluminum in each individual piece. The authors then report the mean, or average, and use this to claim that individuals with autism have high levels of aluminum in their brain. The first major flaw in this paper is that the authors have no controls, that is, no brain tissue from individuals without autism that they compare their measurements to, which alone makes it difficult to accept that these represent high averages for aluminum content. However, the other major issue is how big the standard deviation is. This is showing you a portion of the table that they presented in their paper. This is individual A2, a 50-year-old male. Looking specifically at the parietal lobe, we can see that the 3 pieces of tissue had measured aluminum content of 18.57, 0.01, which was the lowest limit of detection, and 0.64 micrograms per gram of tissue. This is a huge amount of variation. The mean is 6.41 micrograms per gram, but this is nowhere near any of the actual measured values. In fact, the standard deviation is 10.54, which is larger than the average itself. Remember, these are 3 samples taken from the same lobe of the same individual. The fact that the measurements vary so much in those 3 measurements suggests they're not accurately measuring aluminum content at all. Let's take a brief moment and talk about why it's important to look at studies and do this type of critical thinking. Here's a blog post from the website Medium reporting this study as a smoking gun, linking aluminum, which can be present in vaccines, to autism, even though the study itself is highly flawed and the data is so varied you can't trust the aluminum averages reported. Here's another post, also touting that study. Here's one from the publication Business Insider. It's easy for scientific studies that claim major findings to get traction in the popular press, even when they are horribly flawed and have poor quality data. That's why it's important to actually read the studies themselves and not just take a claim at face value. Now let's look at a better example. This is a study looking at the levels of leptin, a hormone associated with hunger. This is looking at the concentration of leptin in the blood of various strains of mice fed a control diet, CD, or a high-fat diet, HFD. You can see that compared to the reported averages, ranging from 17.1 to 57.3, the standard deviations are relatively small, even though they are comparing values from 6 different mice in each case. This suggests that the average leptin values they are reporting are indicative of the leptin concentrations in the 6 mice in each group. What you should be looking for when looking at a standard deviation that has been reported is that the standard deviation should be low compared to the reported mean. When you're looking at data, there's several different ways that the standard deviation can be reported. It could be a standalone value reported on its own in the text of the paper or a figure caption. Sometimes it'll look like this, where they report the mean or the average, and then the standard deviation is reported in parentheses right after. Frequently, it's reported like we're seeing in this paper. The mean or the average is reported, and then plus or minus the standard deviation. And again, it also frequently shows up as error bars on a graph. That ends this video. In the next video, we'll take a look at another number you can use to examine the data presented in a paper.